This is JD Webb for Math 423 Abstract Algebra, video demonstration 2. So the first question is question A2, which is prove that this mapping from R to SL2R, which takes X to that matrix right there, is a group homomorphism, and what is the kernel of this homomorphism? So we have a few definitions and some trig identities here. And given this phi, the homomorphism, or the mapping from R to SL2R by that, show that phi of x plus y is equal to phi of x times phi of y for all x, y, and r. So there's phi of x, there's phi of y, and phi of x plus y. We can say that that's equal to this matrix here. Okay, and we can also show that phi of x times phi of y is equal to the multiplication of these two matrices here, which will give us a pretty large matrix down here. We get cosine of x y minus sine x sine y. Oops, sorry. Yeah, sine x. And here we have negative sine x. Minus sine y, and over here we have okay, and finally we have negative sine x sine y plus cosine of x. And we can use this trig identities up here to show that this is equal to that, this is equal to that, this is equal to that, and this is equal to that. So they're all equal to each other, which means that that is, in fact, a homomorphism. So now we can find the kernel of phi. So find the x in R, where the phi of x is equal to e, which for SL2R is 1, 0, 0, 1. So e equal, or phi of x equal to that e implies that cosine of x is equal to 1, which gives us x equal to n times 2 pi for n and z, which we can see also holds for sine of x equal to 0. So then the kernel of phi is equal to the set of n times 2 pi in R, given that n is now z. And that's the kernel of our homomorphism. So question 2, show that the nilpotent elements of a commutative ring form a subring. So here we have a few definitions of nilpotent in the subring test. And we have here, given a commutative subring R, say that the subset N, which contains all the nilpotent elements, prove that for all A, B, and N, A minus B and A times B are in N. And we can note that A to the N equals 0 and B to the M is also equal to 0 for some N and M and Z plus. So let's first show that A minus B is in N. So A minus B in N implies that A minus B to some R is equal to 0. So let's say that R is equal to N plus M, because we know that A to the N and B to the M are both equal to Z, or 0. So A minus B to the N plus M is equal to is equal to a to the n plus m minus some constant times a to the n plus m minus 1 times b. And this is going to continue on, so on and so forth. But for every term, here, 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 and forever, it's either going to be a to the n times some other term, we can call it g, or b to the m times some other, whatever, h. Since that's 0 and that's 0, all of these terms are equal to 0, and we can say that a minus b to the n plus m is equal to 0. So that would imply that it's nilpotent, and therefore a minus b is in Rn. Next, we can show that a times b is in n. So a times b to some r is equal to 0. So let's say that r is equal to nm. So ab to the nm is equal to a to the nm, b to the nm. And since r is commutative, we know that that can be true. So that's equal to a to the n to the m times b to the m to the n, which is equal to 0 to the m times 0 to the n, which is equal to 0. So AB is nilpotent when nm, which is in Z. So therefore, since a minus b and AB are in n for all a, b, and n, we can show by the subring test that n is a subring of R, and therefore the nilpotent elements of R form a subring.